Let me ask, how many of you took a chemistry class before? Not necessarily, I don't want to ask this before. So a lot of this is going to be familiar. We're really just kind of hitting the top of the topic here. So you know what this is, good old periodic table. Just starting at the beginning of chemistry. Get my clipboard. So what you've got in your hand is essentially a list of all the elements. And very basic information just to start with. What are atoms made up of? 3 things. One of them is electrons. I'll just say electrons, protons, and neutrons. You know the charge on the proton? Charge on the electron? Do you know electrons? These are really usually lowercase, so I'll just. What's the significance of these charges in terms of the way they interact? They do cancel each other, but let me put it like this. As far as a physical force, we call it the electrostatic force. 2 electrons near each other, are they drawn towards each other or do they push away from each other? Electrons repel each other. Proton plus, proton plus. So like charges repel each other. It's when the charges are the same, they attract to each other. And the neutron that doesn't have a charge, it doesn't get involved in this type of force because it doesn't have a positive or negative. Just as a basic fact. Having said that, you can get protons to aggregate with each other, which is a violation of what I just said here. And you can get electrons to aggregate with each other, which is a violation of what I just said here. Really what you have to do is you have to shoot protons towards each other with such a strong force that they overcome that attraction. And when they get close enough, they stick. I've heard it described as if you had 2 magnets that had Velcro on them, and then you turn them to where the poles are repelling each other, and you try to push them and you let go and they'll bounce away. But if you get them close enough, they'll stick. But you have to push with enough force to get them to stick. But this is a fact in atoms, and this is also a fact in atoms. They do aggregate. But in terms of aggregating, you can get electrons to aggregate up to 2 together, but that's it. For electrons, you can only get them to aggregate in pairs. They do have a magnetic, what we call a magnetic moment to them. And it's that magnetic attraction that causes them to stick. But it's sort of like you got a north-south pole and a north-south pole, and they stick, but that's it. You can only get 2 electrons to stick. Protons, you can get them to stick a lot of them together. So, where are the protons in an atom? They're in the middle, what we call the nucleus. So let's pretend I'm building a nucleus here. You can get more and more protons to collect together, but they do have a force of repulsion. Kind of what holds them together, the glue, the Velcro, are the neutrons. But I really want to kind of ignore the neutrons for a second, because we don't talk much about those in chemistry. We'll talk about isotopes, and then we never talk about them. But in terms of an overall view of chemistry. All right, so let's say we have an empty universe, but not completely empty. It's full of protons and electrons, and they're all zooming around the universe. And you just let that go on for a long time. Or it did say that electrons are attracted to protons. Over a long time, let's say somewhere in some corner of the universe, two protons bump into each other with enough force that they stick. So let's say there's this proton by itself over here. There's two that are stuck, and then somewhere in another corner of the universe, one more, there's a pair of protons and another proton managed to stick in there at the right speed. Okay, because of the attractive force, if this one's floating around and another proton doesn't bump into it with enough force to stick, and an electron comes near it first, you'll get an electron to attract to it. And really what it does is the electron floats around the outside. We call it an orbital, but it's like the orbit of the moon around the sun, the orbit of the earth around the, orbit of the moon around the earth, orbit of the earth around the sun. If these two happen to run into a couple of electrons before another proton sticks, then you will have electrons floating around. Let me not pair those though, let me stick them like this. Pairing of electrons follows some certain rules that I'll get to later. And then this might happen to run into 3 electrons. Before any more protons come along. Once these balance each other, meaning this negative charge sort of neutralizes this positive charge, way up close you can see negative right here and positive here. But if you zoom back a bit, this particle as it exists, a proton and an electron, no longer attracts anything. It won't attract electrons, it won't attract protons. Just those 2 protons there floating around, those are attracting, it's a +2 charge. It'll attract any electrons that are nearby. But this won't attract anything anymore. This won't either. This electron and this proton cancel each other. This proton, this electron cancel each other. So this becomes neutral, and this one's neutral as well. So what it would say is, over a I said that these can pair. These can aggregate up to about 100. And then they stop being stable, stuck together. So if time goes on long enough, what's the universe going to be full of? No longer just protons and electrons. What will it be full of? If you let this go long enough. Well, what you'll get is you'll have these floating around the universe, and then you'll have what I call the number 2 atom floating around the universe. You'll have the number 3 atoms. So yeah, when they organize like this, we call them atoms. You'll have 4. And 5. Up to how many? This in a bunch of this in the universe, you have some of that, some of that, some of that, some of that, all the way up to what? What'd you say? These can aggregate up to about 100. So this goes on up to about 100 protons, 100 electrons, like that. And that's what you have in your hand, the list of all of those things from the universe. I said about 100. It is a little more than that, but I'll get to the periodic table in a little bit. But most of these way down here on the bottom, we kind of ignore that, especially for introductory chemistry. Those are exotic, they're very rare, they're all radioactive. We just, as chemists, we're almost always dealing with stuff up here near the top, and a few of these in the middle here. But these down towards the bottom, we probably won't even talk about at all, because they're so rare and they're radioactive, and we don't tend to. Most things in your world, the crust of the earth is made up of things towards the top and maybe a few towards the middle. So those are atoms. That's what atoms are, and that's where they come from. Truthfully, most of them are made inside of suns, not the way I just described. You could call this the number 1 atom. You could call this the number 2 atom, just because of the number of protons and electrons. I guess you could call that 100, but let me stick with this sequence. smaller sequence for now. All right. This number, later we'll talk about how atoms can lose some electrons and gain some electrons and they end up being charged. For now, let's just stick with these. And let me say this, kind of the first important definition is, this number I'm going to call the atomic number is 1. The atomic number refers to the number of protons specifically. So this atom, we'd say atomic number 2, that's telling you that there are 2 protons in the nucleus. Like I said, later we'll talk about where, say this atom might be able to lose its electrons and just be this, but it's still this atom, it's still the number 2 atom because it's got 2 protons. Let me try, let me jump forward for just a second to say, there's 9 protons. And there's 9 electrons. That would be neutral. The atomic number of this would be what? What's the atomic number of this?
9.
It is 9, and that's because it has 9 protons. This is atomic number 9. Atomic number 9. So just get used to that definition of atomic number. And I chose this one because it can actually gain an extra electron, and I'll get to the rules. So now this has 10 electrons. Now what's its atomic number? It's still 9. That's the point. The atomic number, you can gain and lose electrons. The story of chemistry is all about the electrons. So we talk about protons and neutrons early on in a chemistry discussion, and then we'll just kind of leave it alone and talk only about electrons later. But the fact that it can gain and lose electrons means using electrons as a definition for its identity is not useful. But the number of protons never changes. You can get numbers of protons to change. You can split apart atoms and you can fuse, say, 2 of these together to make this. But that's nuclear science. That's really a physicist's domain. You've heard of nuclear energy and nuclear bombs. So that's what they're doing. They're either fusing atoms or blowing them apart. In chemistry, we never talk about splitting the atom. So whenever you see atomic number, it tells you how many protons are in the nucleus. The particular atom you're talking about may have gained or lost some electrons, but still the number of protons there remains the same. If you look on your periodic table, you see in the top left, you see the 1 that's there, just the integer 1. And you go way over to the right side, you see the integer 2 there. And then you come back over here, you see the integers 3, 4, 5, 6, 7, 8, 9, 10. Those are the atomic numbers. So kind of your first orientation or reorientation to the periodic table is that number on the periodic table is the atomic number. I guess you have a diagram here that helps you see that. I like this periodic table. I downloaded it years ago and saved it because it has something else on here that I don't like to make people memorize. Just because memorizing is, you don't need someone to stand in front of you and talk. When it comes to memorizing, you want someone to explain things. Atomic number 1. So you see that here, that's that 1. That's literally a synonym for the word. We didn't have to call that hydrogen. Oh, and then it's also a synonym for this, the atomic symbol, which is also. So all those first 3 things, there's hydrogen at the top, a 1 and an H, those are all synonyms. They all mean exactly the same thing. Hydrogen, atomic number 1, and H they all mean that. Or really, they really just are referring to this, because you can lose that electron. So they're referring to a nucleus that has one proton. You follow that? So those three things are really denoting the exact same thing. The 1.01 in that box and the 2.1 we'll get to later. But as far as using this, that orients you to a little bit of facts about the periodic table. And if you took a chemistry class before, I realize this is all very obvious to you, but I'm not going to assume you took chemistry before, so I'm just going to go through all of it. So having started there and given you this, the periodic table, if we kept looking at it, there's something else about the periodic table that is very useful. Of course, the world is not made up of only atoms. Atoms come together to form compounds. So the next thing I would tell you is to look at the periodic table. You see this stair step structure here? It goes like this. Right there is B. This section Okay, so those of you who have taken chemistry before, which were a lot of you, not counting these, do you know what those were called on the far right? Remember what they're called? Noble gases. So not counting those, you guys, not counting those, and above this stair step, do you know what those are called? You're close. They're either metals or non-metals. Non-metals. So this upper right triangle, not counting these, and everything else are metals. So, truthfully, along this jagged line, you remember there's one more thing. There's metals, there's non-metals, and there's one more. There are some that are called metalloids. And if you think about these stair steps, above and below each one of these, not all of them are metalloids, but almost all of them. Aluminum is an exception. Aluminum is a metal. I'll just leave it at that. So not really counting the metalloids that are right along here. These in here are the non-metals. And everything else over here are metals, including aluminum. So when it comes to metals and non-metals, which is where I'm going to focus, you got your, not counting the noble gases, you got the upper right triangle, that's the non-metals. And everything else is metals. And there's one exception to this, and there's one exception to this. There's one other non-metal on the periodic table. Do you know which one it is? It just doesn't happen to be up there on the right. Anybody? Yes, hydrogen. And the exception to the metals is aluminum. So aluminum is a metal. Hydrogen is a non-metal. And then there are a few metalloids, and I'm just not even going to talk about it. They behave like a metal sometimes, they behave like a non-metal sometimes. So they're kind of weird. Okay, that definition, metals and non-metals. I should say. So now I'm going to talk about this idea that electrons can vary. Do you remember this? Non-metals blank, sometimes blank electrons, and metals sometimes blank electrons. Remember which is which? Nobody can remember your chemistry. Non-metals will sometimes gain extra electrons. And metals will sometimes lose electrons. Okay, following here, it says, okay, all the compounds in the universe that exist fall into four categories. All across the universe, there are only four possible types of compounds. And they're fairly different from each other. And truthfully, we're only going to talk about one of them. I mean, two of them. We'll talk about metallic a little bit. But a metallic compound is made up of no nonmetals and, yes, only metals. So if I had a compound and I listed the atoms that are in the compound, if you don't see any of these at all, then you're talking about a metallic compound, which we won't talk about very much. I like to bring this up because it's what you already think of as a metal. They're hard, they go plain, change is made of them. This is a metallic compound. This door handle, this plate, what you already think of as a metal, that's a metallic compound. And we don't talk much about those. Coordinate covalent is kind of weird, don't worry about it. We won't talk about those at all. We're going to focus on ionic and covalent compounds. And given this chart that I've made, covalent compounds and don't worry about this. I just like to put it because this is a complete list of all the compounds throughout the entire universe. Metallic has only metals. Covalent has only nonmetals. So what do you think ionic does?
What? I'm sorry. What does that thing say underneath metallic?
Coordinate covalent, but don't worry about it.
Okay.
I won't even put it on a test.
Okay.
I probably won't put anything about metallic on a test either. This is where we're focusing. I just like to do this because it's a complete list and there's only 4 of them. And there's a system here I want to refer to. Metals have only metal. Covalent only has nonmetals. So what do you think ionic has?
Metal.
Huh?
Metal.
If it had metal only, then it would fit in this category.
So both.
Huh?
Both.
Yes. This is what makes something ionic. It has one or more from here and one or more from the metals. And if you're looking at the formula for something and you see that there's one or more metals there and one or more nonmetals, you know that it's ionic. If you look at it and it only has metals from the periodic table, it's this. And if it only has nonmetals from the periodic table, it's this. Just as it is. Okay. So first, an introduction to ionic compounds is an introduction to ions. So we'll talk about ions and how ionic compounds are created. More of a periodic table. Oh, yes. Yeah, whatever you need. Can I just look for something in there real quick? The extension to this, I think it's in there under your prison. Let me run in there. Be right back. I'll see if I can get the camera closer.
Well, I think John.
Oh, he is? I'm going to get an extension for that so it's closer, so the board takes up like all it is. All right. So when it comes to ions, what have I talked about already that refers to ions? This. And if it does lose, it is in ions. Let me put it like this. Let let me go back to remember this example? 3, 4, 5, 7, 8. I've kind of skipped over neutrons. There can be neutrons in here, but I'll come back around to talking about those. So this atom, what's the atomic number for the atom that has those protons? What's the atomic number? 9. If you look on here, which one is it? Yeah. So that's fluorine. And it's neutral. When it's neutral, 4, 5, 6, 7, 8, 9. You have this many electrons floating around it. Is that 9? This would be neutral. If it's covalent, all the atoms are neutral. So fluorine might show up in a covalent compound. But let's talk about fluorine when it shows up in an ionic compound. Fluorine has a tendency to gain one more electron. So now I have 9 protons, 10 electrons. So the overall atom now has a charge on it. For every proton that's here, it cancels one of the electrons. So when there's 9 protons and 9 electrons, it's neutral, like I said before. But if you get an extra electron, each proton is canceling an electron, but if you cancel, you get down to where you've used all the protons to cancel the 9 electrons, then you've got one more extra electron. So the ionized form of fluorine, called fluoride, we'll get to naming later, has a charge of -1 on it. And the way we would write that is F negative, I'll say -1, F -1. You see what I'm saying? If atomic number 9 atom, that is fluorine, gains an extra electron from its neutral state, it ends up being -1 because these are negative. So this proton cancels this electron, this proton cancels this one, this proton cancels this one, cancel, 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 and we've got one left that we can't cancel. So when fluorine gains an extra electron, it's got a -1 charge. For some reason, chemists say 1 negative instead of -1. I go back and forth. If I did oxygen, well, scratch all these out. If I wanted to build oxygen, so here's fluorine. If I wanted to build oxygen, let me build the nucleus, just the protons. How many am I going to put in here? 8, because it's atomic number 8 on the periodic table. 1, 2, 3, 4, 5, 6, 7, 8. Here's neutral. So those are the electrons going around the outside. That's neutral oxygen. It has no charge. But oxygen has a tendency to gain 2 extra electrons. And I'll tell you the rules, how I know that it's 2. But so this would be neutral oxygen, and I would just write that as O for the symbol. So now I've got 8 protons and 8 electrons. Oxygen tends to gain 2 electrons. So here's an extra one, and here's an extra one. So since I've got 2 extra ones, now it's got a 2 charge, a -2 charge. You with me? This all seems very familiar. All right, so each proton here cancels an electron, but we run out of protons and we have 2 extra electrons, so we would say 2 plus. And I did that just to say there's several places in chemistry where if it's 1, we just don't write it. So really, truthfully, we write fluorine like that to indicate -1, and then if it's more than 1, we actually put a digit there. It's a little weird, but chemistry drops to the 1 in a lot of different situations. Okay, you guys with me? Okay, so I'm talking about ionic compounds here. This is what I want to talk about. But sort of the hallmark of ionic compounds is what happens first is there's some gaining or losing of electrons. So we've had charged things, and then these charged things are attracted to each other. So these are nonmetals, and I talked about them gaining electrons. Let's talk about some metals. So there's that wide part here in the middle of the periodic table. And I want to skip that wide part for now and just go over here to these first two columns where I've got hydrogen. And these, let's fill these in. Oh, by the way, I will give you that chart that you have in your hands on any test we take. So you don't have to memorize it. It might help to familiarize yourself with a few of the top rows, just to save yourself time hunting around looking for stuff. See this. Lithium, radon. So I'm going to ignore this metal part for now. Okay. So everything in here are metals, and these are metals. These are called transition metals. These are just called metals. These are called post-transition metals. Just nomenclature. And these are kind of weird and they don't quite follow the rules. They're kind of like the metalloids. So really, everything we're going to do, we're focusing not on these, but on the non-metals, including hydrogen, and then metals from here and here. And the rest just gets too weird to cover. So really stuff along here and then here. It's this upper right triangle. Noble gases will come up a little bit, but this is where we're going to be. Okay. So I already said metals tend to lose electrons. So let me pick magnesium. Magnesium. How many protons are in a magnesium atom? That's on the left side. It's Mg. This one. What's the atomic number of Mg? So I'm going to draw the protons in its nucleus. How many are there? You know what? Let's do beryllium, just to save me a bunch of drawing. Beryllium. What's the atomic number? What is it?
4.
1, 2, 3. So there's the nucleus without the neutrons for beryllium. And I want the neutral one, so I'm going to draw 4 electrons going around. Neutral beryllium. If you have neutral beryllium in a compound, it's going to be a metallic compound. Metallic compounds don't have charges. All the metals that are there are neutral. So if you had beryllium in a metal, it would look like this in the metallic compound. But let's talk about beryllium in an ionic compound. Beryllium tends to lose 2 electrons. So I'll kick out this one and this one. Now it ends up charged just the same as the nonmetals would end up charged. But this time, cancel a proton, cancel electron, cancel electron, cancel a proton. Now we end up with 2 positive charges left over. So metal, it lost electrons, specifically it lost 2, so now it's a +2 charge. So, and I said before, oxygen would be -2. Did I say that? I did, didn't I? No, I probably wrote 2 negative, but anyway. If you have beryllium, and it loses 2 electrons, and you have oxygen, and it gains 2 electrons, these two will be attracted to each other because you got positive and negative charge. See what I'm saying? So they'll come together and they'll form a compound that we would write like this, PeO. So there's your first compound in this rehash of chemistry in your life. It's an ionic compound, and it came together literally because of the charges. The electrostatic force pulled them together. Covalent compounds don't have this. You guys with me? Okay. Let me do another one. Okay, let me tell you the rules. If you want to know what the charge is, so these can be neutral. And if you have a compound only of these and maybe hydrogen, and they're all neutral, you necessarily have a covalent compound. If you have something that has some of these and some of the metals, you necessarily have an ionic compound, and everything is in its charged form. It's in its ionic form. But staying with ionic compounds, ionic, coming up a little bit. Here's the rules. We'll talk about valence electrons, and I may get to that today, I don't know. But here's the quick rule to remember. Everything in this column, not counting hydrogen, that goes with those, but all of this in this column, they lose 1 electron. Everything in this column, lose 2 electrons. There's one more. Remember I said aluminum is here, and then everything else is transition metals and post-transition metals? This is the weird one. This one is 3 electrons. So in terms of metals, if I said, what is the charge on this when it's an ion? The charge is going to be what? If it loses 1 negative charge, everything in this column. Well, what was the charge on beryllium? Beryllium, proton, 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 electron, 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 electron. If it loses 2, then you have cancel, cancel, you have 2 leftover positive charges.
Oh, so that was +1. Oh wait, are those people +1 and +2, +3 groups? Like a color mass?
Yeah, if that's the way you think of it. But the idea is everything in this column will lose 2 electrons to become +2 charge. Everything in this column, when it's an ion, will lose 1 electron and it'll be +1. You guys with me? And when this one loses its 3 electrons, it's 3 plus. So another way to say what metals are is when they're in their ionic state, they're positive. Okay, the rules for this side. You do this. If I wanted to say what's the charge on nitrogen, you put your finger on nitrogen, but you don't count it, and you go to the right. So how many electrons does nitrogen gain? It gains 1, 2, 3. Sulfur, how many electrons does it gain? It gains, I'm not going to count this one, but I'm going to put my finger here. How many electrons does this gain? You go 1, 2. So everything in this column will gain 3 electrons, which will make it 3 negative. Everything in this column, not counting down here, I'm ignoring these, but these up here, these gain 2 electrons, 2 negative, 1 negative. Ignore those don't count. And in the rare case, this one would be 4 negative. carbon and silicon ionized. Those are the rules. So these, when they're an ion, will be +1. These, when they're an ion, will be +2. These, when they're an ion, will be -4. These, when they're an ion, will be -3. These, when they're an ion, will be -2. These will be -1, and ignore the noble gases. They don't become ions. You got that rule? Okay, so let me ask you this. Looking at your periodic table, when it's an ion, what's the charge on lithium? It's negative.
+1.
+1. I'm not going to write the 1 just to. If we have magnesium, what's the charge on it when it's an ion? 2 plus. Let's grab an extra one here. Let's do potassium. So it'll be K plus. And let's do calcium too. What's the charge on calcium? 2 plus. What's the charge on chlorine when it's an ion? 1. What's the charge on aluminum when it's charged?
3.
Aluminum is 3 plus. How about sulfur? Sulfur. What's the charge on sulfur? Negative what? 2 negative. I should write all these just to be consistent. I'll say -2. Nitrogen. 3. Nitrogen. 3 negative. I won't be consistent, I guess. Fluorine, that's the F. F will be negative. And I like oxygen. Let's just put oxygen here too. So I'll give you a fresh one of those periodic tables for a test. It wouldn't hurt to write some notes on it now while you're doing it, but you won't get yours back. You'll get a fresh one like that. So just realize those are the rules for gaining and losing electrons. And now we can talk about ionic compounds. I guess I won't get the covalent today. I was losing electrons. Oh, by the way, if you gain electrons and you're negative, you're covalent. And gain electrons and you're positive, you're a cat. I saw this meme somewhere. It's supposed to be a paw. I can't draw a cat paw. You want to remember, cat ions are positive. Remember this. Let's say I have lithium and oxygen, and I tell you, I'm going to make an ionic compound out of these. So the first thing you know is lithium is charged. What's the charge on lithium? Lithium is +1. What's the charge on oxygen? 2 negative. If I'm going to make a compound out of these, the ionic compound that you build has to end up being neutral once you stick everything together. So the only way to bring these together and make it neutral is to have 2 lithiums. So now you've got a total of 2 plus and a total of 2 minus. So I have to put these together to make the compound. You with me? That's how you make the ionic compound. You with me? The way we would write that for a formula is Li2 ion compound made of lithium and oxygen. If I made an ionic compound of Mg and F, what would the formula be? What's the charge on Mg? You have to go through this thought process. 2 plus, and what's the charge on fluorine? -1. Taking away your cheat sheet. All right, so to make this balance, we're going to have to have 2 of the fluorines. That way I'll have 2 negative charges, and they will balance this charge. So that would be ionic compound made of magnesium and fluorine is MgF2+. You guys with me? These are all usually pretty straightforward. We do it just like this. But well, let me just do, what's the charge on aluminum? I erased your cheat sheet. It's over here. It's the 1 plus 3. And let's do chlorine. What's the charge on chlorine? -1. So we're going to need 3 of these to balance the aluminum. So your formula is going to be 1 Al and 3 Cl. Oh, yeah, this is another situation. You would think I would put a 1 there, but this is another one of those situations where chemists like to just not write the 1. There should be a 1 there in some sense, but chemists just don't write the 1 when there's only 1 of them. So that's that. You would think there should be a 1 there, but we just don't write the 1 when it's just 1. It's a weird quirk, but it keeps things straight if I say it out loud. So we've got these formulas. We'll get to how you name these. We've got to do a little more here. But if you walked in here next week and I put this in front of you and said, is this an ionic compound or a covalent compound? The way you can tell is it has a metal and a non-metal, then it's ionic. Metal, non-metal, metal, non-metal. Oh, and by the way, when we write these formulas, we always put the metal first. So we go metal, non-metal, metal, non-metal, metal. Okay, the only weird one of these that show up, what if I do aluminum? What is the charge on oxygen? 2 negative. What's the formula for that? How do you get those to balance? Yeah. Oh, did you say 2 oxygens? This is kind of like least common multiples. You can't just have 1 of these and some multiple of these. You can't get them balanced. And you can't have just 1 of these and some multiple of these. It won't balance. So now you're going to have to build them up some. But the magic number you need to remember is 6. If you get 2 of these, like the least common multiple of 3 and 2, that's what you have to do. Now you got a total of 6 negative charge and 6 positive charge, and the formula would be Al2O3. And that's really the only time you run into something weird. When we get to the transition metals, they can have much higher charges, and maybe you run into the same situation, but it's always sort of the least common multiple that you can come up with. And I can do this the other way around. What's the charge on, this is sodium. What's the charge on Na? +1, I won't write the 1. And let's do nitrogen. What's the charge on nitrogen? Oh, no. Well, what would be the formula for this one? You need 3 NAs. balance that for you, so it would actually be NA3. Yeah. I could see NA3-1, but we don't write the 1, so that would be the formula for sodium nitrogen.
Does,
Um,
does like butterfly method work for like all of these? Or
What did
is
you
it
say?
like the but where you just switch them? Like you break like the A.
When it's
plus
2 and 3, you can.
2 and 3, okay.
I'd have to think if you got to charges higher than 3,
Yeah.
if that always works, because then there might be, but anyway. For what I'm talking about here, yeah, you call it the butterfly method.
Yeah.
High schools come up with so many cute things. Oh, thank you.
I don't know Westbusters.
Oh, really? Here? They did it here? It's very cute. I'll come up with a special name for it.
Yeah.
There's enough naming chemistry. So that's the logic, but let me do this. What if I did this? What's the charge on calcium? Yep, this is 2 plus. So this is the same situation when we've got a 2 here and a 3 here. Over here, we had a 3 on the metal and a 2 on the non-metal. Here we have a 2 on the metal and 3 on the non-metal. But it's the exact same idea. I'm going to get 2 of these and 3 of these. So this one is going to be Ca3N2. But yeah, you can think of it as swapping the 2 and the 3 if you like. But that's the logic in it. Just as long as you get them to balance, you'll come up with the right formula. Okay. Everything I've talked about so far, well, I could point at an atom and say, what's the charge on it? I taught you the rules, and y'all will tell me the charge. Let's talk about the transition metals, because those get weird. So, do you remember what's weird about the transition metals in this context? The thing about transition metals is many of them can take on more than one charge. So beryllium is only ever going to be +2. All of these are only ever going to be +2 in ions. These will only ever be +1. Aluminum will only ever be +3. The non-metals, there will only ever be what I've told you they'd be, -3, -2, -1. Transition metals, for instance, there's such thing as Fe2 plus and Fe3 plus. All right, so if I said I have Fen, what would you infer the charge on iron is? If I said that's the formula, what did you say?
3 plus?
Yeah. Nitrogen is necessarily 3 negative. If the formula is written like that, then I'm talking about Fe3 plus. There is another Fe2 plus, and if I did that with nitrogen, it's going to be Fe3 and 2. So in this case, Fe is 3 plus. In this case, it's Fe2 plus. You follow that? Okay, there's one more type of ion that I'm going to save it. You remember polyatomic ions? SO3, SO4. I'll come back to that because those are actually covalent compounds that happen to be charged. But let me say this. The nonmetals. You see carbon there above the C, carbon. I'm going to call it carbide. This. Nitride. Oxide. Fluoride. I won't do silicide, that's too rare. And let's go down. Iodide. There is Telluride, let me just stop there. Okay. On the periodic table, you see carbon, but I've said the word carbide. You see nitrogen, but I've said nitride. When you name these, and I'm not talking about transition metals here, just let's say it's these metals or aluminum, because those are the ones with the predictable charge. If you're naming, if I name this, the metal is what you see on the periodic table. You just name it as the metal that it is. So this is called magnesium, but it's not called magnesium fluorine, it's called magnesium fluoride. So you can just call this the magnesium ion, magnesium ion. This is fluorine, this is called fluoride. So this is how you name these. So what would be the name of CaCl2? Oh, by the way, let me say it just so you don't miss. You see this too? You might be tempted to say magnesium difluoride. You don't use mono, di, tri, tetra when it comes to naming ionic compounds. You do that with some of the covalent compounds. So don't use those when you name ionic compounds. I inevitably see it on the test. Somebody names this magnesium difluoride. If I give you A, B, C, D, E choices, I'm going to put magnesium difluoride on there and see if I catch it. So don't use mono, di, tri. So what would be the name of this?
Calcium.
So it's going to be calcium right off the periodic table. And what's the next word? Chloride. So it's that simple. You use those with the names off the periodic table. You name them. When it comes to the transition metals, let's do Fe. So if we're naming these, what would you call this? Oh, F is iron, Fe is iron. So we use the word iron for those. So that's the metal, it's a transition metal. You're going to go iron what? Nitride. I'm going to leave a gap here. And this one, you would come up with the same name. Iron nitride. So if I sent you to the stock room and I said, go get me some iron nitride, you'd head in there, but you'd stop short and go, wait a minute, does he want this or does he want this? I should have told you one more thing. I should have said, it goes here, we put it in parentheses. Do you know what it is? Well, what's different between these two that needs to be specified? Huh? They're both balanced. The thing about, I said it quick and I went past it, but the thing about the transition metals, iron Fe is in the transition metals, it's right here. The thing about the transition metals, they can have more than one charge. So what's the charge on Fe here? So nitrogen is -3, and I've got one of these, so this must necessarily be +3. All right. And what's the charge on fluorine? What is it? +2. So that's what goes here. But you do it in Roman numerals. So what I should have told you when you went to the stock room, I said, go get me some iron 2 nitride. Because then you know what you're going to do. So when you're naming them that have the transition metal in it, you put the charge of the metal ions here, and then you can distinguish what the name between the two is. All right, good. There's your introduction to chemistry. If you care to see it again, I'll upload it.